Oh, so graphing. Let's just go over things that we should already know. I guess we started with the idea of basic curves, just recognizing a basic curve, and then we can, shift it across and up and down and all that sort of thing. So the basic curves, we've got straight lines, y equals x being the most basic, of course. And for some reason you didn't recognize it, you go, oh, look at that. Both the powers of the pronumerals are 1. So we have a linear function. Then we moved on to quadratics, so our parabola. And all of a sudden, one of the pronumerals was to the power of 2. In general, of course, we have y equals ax squared plus bx plus c. We did a whole heap of work on quadratics. Cubics, basic one, y equals x cubed. So one of the pronumerals will end up being to the power of 3. General cubic, ax cubed plus bx squared plus cx plus d. And then we said, okay, well, let's look at polynomials in general. We did a whole heap of work on polynomials. So we should recognise all those sorts of shapes. Hyperbolas. So it's where you see, pronumerals multiplied together, x, y, or you have a pronumeral in the denominator. That usually creates some sort of hyperbolic function. Exponentials. That's kind of a giveaway. We see one of the pronumerals in the power, or as we sometimes call it, the exponent, hence the name exponential. Circles, of course. So the basic one, x squared plus y squared, is the radius squared. Now both of the pronumerals are to the power of 2, but also the coefficients are the same. Because if they're not the same, we get our ellipse. Well, that's if they're the same sign. If the signs are different, then we know we have our hyperbola from what we saw with our extension work on conics. Logarithmic curves, how do you recognise that? The word log is usually a giveaway. Trig curves, so similar, you see the sine, the cos, the tan, etc. And I guess the last type of function we looked at was the inverse trig functions. So these are all functions we should recognise their basic shape. Okay. Then there was the idea of symmetry. If we recognised it was an odd or an even function, we knew, where are we? Odd function. Well, the formal definition, function negative x is equal to negative function x if we have to prove it. But that one has rotational symmetry. So symmetry about the origin. Even function, function negative x equals function x. That one has line symmetry. So the y-axis is the axis of symmetry. Now, we didn't talk a heck of a lot about this. Probably comes more into play when we were talking about inverse functions. Symmetry in the line y equals x. Remember, inverse functions are reflections in the line y equals x. So therefore, if you swap the x, y's around and it doesn't change the function, then that curve must be symmetric in the line y equals x because it is its own inverse. So an example of that would be something like that. X cubed plus y cubed is equal to 1. The idea of dominance, okay, and that's useful when x is becoming really big. When x is becoming really big, does a particular part of that function dominate? So in a polynomial, the leading term will always dominate. And that's why when we were drawing polynomials, we just looked at the leading term and said, well, where does that one start and finish? So what's happening at negative infinity and infinity? Because the leading term dominates. So in y equals x to the 4 plus 3x cubed minus 2x plus 2, to know where it starts and finish, I just have to look at the leading term, x to the power of 4. So I know over at negative infinity it starts up in the positives, up high, and over at positive infinity it does too, because that's how you would draw y equals x to the power of 4. Why does it dominate? Remember, theoretically, you're substituting in infinity, and you can't actually substitute in infinity. So when you're dealing with such a large number, x to the power of 4 is just so much bigger than x cubed or x that they become insignificant. Exponentials will dominate. What you're really looking for is which term increases the most rapidly. And if you think of an exponential curve, that really increases rapidly. So if you've got something times an exponential, then the exponential is going to dominate in that term. So as I say, in general, look for the one that increases the most rapidly, so which is the steepest. And of course, if you're unsure, there's nothing stopping you subbing in a really big number, and then you can see what's happening out at infinity, and you start getting a feel for it. And if you sub in something like, what did I put there, 1 million, and you can't tell, sub in 10 million. See what then happens. Is it getting bigger? Is it getting smaller? Is it going towards a constant number? Okay, asymptotes. We know about vertical asymptotes. So bottom of the fraction can't equal 0, usually creates most of them. In trig curves, of course, it's a little bit different. We know tan x has got a vertical asymptote. Horizontal and oblique asymptotes. So top of the fraction is a constant. The fraction can't equal 0, so that's an idea we can use for that. Limits as x approaches infinity. If it's a horizontal one, that'll work that one out. Remember, if you got the order of the numerator is greater than or equal to the order of the denominator, do a polynomial division first, and that'll bring out the asymptote for you. Our special limits. And it's actually a 2-unit limit, although you never really get questions on a 2-unit. You do tend to get it in 3-unit, but it is technically a 2-unit limit. What's that one? Limit as x approaches 0 of sine x on x is equal to 1. Then, after we looked at all the ideas of basic curves, we looked at this thing called calculus, and that allowed us to do even more with curve sketching. In this topic, a lot of the times we won't use calculus. A lot of it's just sketches and we've got a good idea. However, that doesn't stop us using it as a tool. So critical points, stationary points, inflection points, obviously calculus will find those out for us. So what's a critical point? When the derivative is undefined, right? We know it will have a vertical tangent, or it doesn't exist at that point, one of those two I suppose. But if it exists at that point, then we're going to have a vertical tangent, because we're saying that the gradient function is undefined, which is like saying it has an infinite slope. So we call those points critical points. Now, technically, stationary points are critical points as well, but we call them stationary points rather than they've got their own special name. So when we think of critical points, we tend to think of the ones with vertical tangents. So speaking of stationary points, well, that's when our derivative, of course, is equal to 0. We end up with our horizontal tangent, and they might be maximum, they might be minimum, might, of course, be a horizontal point of inflection. So maximum, minimum turning points, well, that all had to do with the concavity then. Once we've determined, yes, it is a stationary point, we then use the second derivative to say, oh, well, it's concave up or it's concave down. And from those two things, we can put it together. If it's concave up, it must be a minimum turning point. If it was concave down, it must be a maximum turning point. Now, depending on the function, I mean, if it's going to be a difficult thing to differentiate, don't find the second derivative. Just test either side of your stationary point and sub in and see what the tangent's doing. So is the curve increasing, then decreasing? Oh, well, that's got to be a maximum, or vice versa. Inflection points. So that's when the second derivative is equal to 0. A lot of these you just test either side, but if it's a simple thing to differentiate, we can look at the third derivative and say, oh, hang on, that does not equal 0. Because what we're saying is the change in the second derivative does not equal 0. Therefore, there must be a change because it has some value. As I say, again, sometimes it's quicker to test either side of the second derivative. Now, if you've got all of those conditions, yes, it's a stationary point and it's an inflection point. Remember, that's our classic horizontal point of inflection, the most common one being our y equals x cubed, our cubic there would be a horizontal point of inflection. But remember, not all inflection points are horizontal points of inflection. So when you're drawing your graphs, if you've got an inflection point, don't try and force it to be a horizontal one. It might not be. Just draw the curve naturally and it should just fall out. Okay, increasing, decreasing. Well, first derivative is handy for that. If we've got a positive slope, we know the curve's going up, so it's increasing. If we've got a negative slope, the curve must be going down. We know it's decreasing. And then this idea of implicit differentiation. If we don't want to make y the subject, then we can differentiate implicitly. So let's go back to x cubed plus y cubed equals 1. What does it look like? Okay. So as mentioned before, it has symmetry in y equals x. I know that. So there's y equals x. I know it's going to be symmetric in that line. Now, some of the easy points to find. X-intercepts and y-intercepts. Passes through 1, 0, but also passes through 0, 1. Well, that makes sense. We just said it was symmetric in y equals x. So let's plot those 2 points. Okay. Now, this might not be immediately obvious, but it is actually asymptotic to the line y equals negative x. How do I know that? Okay. A little bit of working out here. If I rearrange that and make it y cubed equals 1 minus x cubed, well, that means y cubed can't equal negative x cubed, because it's always going to be negative x cubed plus 1. So it gets very, very close to x cubed, but it's always going to be 1 away from it. Well, therefore, y can't equal negative x. So it becomes an asymptote. Let's differentiate implicitly, see if we can find stationary points and so on. So x cubed becomes 3x squared. Y cubed, well, remember, I can't differentiate that with respect to x, so I differentiate it with respect to y and multiply by dy dx. We end up with dy dx is equal to minus x squared on y squared. So in order to work out the gradient, I need both the x and the y values. Well, what does it mean? A few things there. That derivative always has to be negative, because I've got x squared on y squared, but minus that. So therefore I know this curve's always decreasing. But it's at 1, 0, get this the right way around, 1, 0 is going to have the vertical tangent, isn't it? Because that'll give us 0 on the bottom of the fraction. And 0, 1 will therefore become a horizontal point of inflection. There's my graph. Now, how did I know that straight away? Well, if this was a vertical tangent, remember, if we're reflecting, I must get a horizontal tangent at 0, 1.